Hello, everyone, and welcome to our 2024 Design Expo video. We are the General Expedition Adventure Research Enterprise at Michigan Tech, also referred to as GEAR. Our small team is comprised of 4 students, predominantly from the Mechanical Engineering Department, with 1 robotics engineer. During this presentation, each member will speak on the role they led within the team with the support of the other members. GEAR offers students the opportunity to apply team and engineering skill and application revolved around student personal interests in outdoor recreation, though our specific focus is on commercial recreational equipment related to backpacking, camping, kayaking, and mountaineering. The enterprise seeks to partner with industry leads in product development and manufacturing innovation through direct consultation, while allowing students the opportunity to apply their skills. This first image is a mountain bike trail extrication device, which was designed a while back, which is one of our previous projects. Next, we have the sit ski. And lastly, we have the avalanche beacon.
Stormy Kromer, headquartered in Ironwood, Michigan, is a renowned Midwest-based custom hat producer, most famous for their wool caps. These caps were originally created out of necessity for warmth during winter, but have since become an iconic tradition in the Midwest. Stormy Kromer recently approached our team with a challenge: inconsistent hat measurements during end-of-line checks. Our project goal is to devise a quantitative system that accurately assesses hat size and fit for Stormy Kromer. This involves studying hat fit among various demographics, analyzing manufacturing methods, and crafting a functional prototype for end-of-line inspections.
To lay the groundwork for our project, we first researched existing hat measurement devices. This included like tape measures and scissors types as shown. We found out that these devices didn't have a constant force because many hats would, the same hat would be measured at different sizes using the same device. So we created a hat fitment device to determine a constant force for our planned DAC system. This was using elastic stretch and spring constants. Then we dived into rapid design and prototyping using Autodesk Fusion 360 and Lubon 3D printers. Some design iterations are shown here. How our design works is the motor spins to linearly expand and contract arms along a spiral cam. Throughout these iterations, we've reduced the number of arms, the arm lip and curvature for hat placement, and the tracks to reduce friction. During this year, we finalized the design to make it robust for installing in a manufacturing facility. This included making the legs simpler, just using rounded legs to manufacture easily, and also had the arms being dome shaped to better place the hat. A big part of this year was to develop a control box. And this included laying out the buttons, such as the e-stop, power button, and the reset and go button. Also to account for the electronic plugs. Some other CADing that happened was for the electrical components. This included cases for the Arduino and Shield, the LCD screen, and breadboard, and along with the e-stop spacer.
The fabrication process has multiple steps, which I broke into 3 categories. Firstly, rapid prototyping was done utilizing 3D printers due to their precision, ease of creation, and speed. Following the assembly of the prototypes, the tolerance, fitment, design integrity, and functionality was tested. At this stage, multiple design changes were made throughout the project timeline, which can be denoted in the project background slide. This year, team members completed all cuts, welds, etc. with the help of Martin Tooth, training specialist supervisor in the shop. Each part was made out of and produced based on the specifications under device machining. To create the arms, welding was necessary to conjoin the hemisphere pieces and CNC precision cut plates. All metal components were then sanded and assembled utilizing hardware added to the initial CAD model. The electronics box was then machined by programming the CNC per the drawing developed from the model. Lastly, customized holders were designed and 3D printed to best fit the electronic components. Here are 2 images of our current product that we have completed and machined.
The programming on the hat fitment device was done entirely with Arduino IDE, as well as using the built-in libraries for the motor controller and the LCD screen. Seen above is a process flowchart of what the hat fitment device is supposed to accomplish when running correctly. This diagram was used to help develop the code that we are currently running. The fitment device starts the process when the green start button is pressed. From here, the motor controller will rotate the motor in a positive direction. The first decision point of the code is to make if there is a pressure sensor is activated to tell if the device has reached the correct hat size. If for some reason an error were to occur, the motor would be limited by an encoder value that will be defined. From here, the hat size is calculated and outputted to a digital readout on the LCD screen. Next, the user will have the option to reset the hat device to read another measurement. If the reset button is pressed, the motor will start spinning in the opposite direction. The final decision node is a limit switch, which acts as a failsafe as well, and to tell if the device is at 0. If this limit switch is pressed, the code will end and the process is over.
So these 3 images show the electrical work that has been done throughout the semester, with the left being the prototype on the Arduino to make sure the motor works and to test the encoder data, as well as the 2 control panels on the middle and the right side. All this is a simple feedback system that communicates between the Arduino, reading the encoder data, and then telling the motor to spin to a certain position based off of that. This whole thing operates off of a 12-volt architecture with each of the 4 components using that. The big box, the metal one, is the power supply, and then we also have a voltage regulator module, an Arduino, and then a custom-made PCB that helps to make sure that everything functions properly. Overall, this whole device has about 15 data lines to communicate between the Arduino and the hat device, so that we can be as accurate and precise when making sure that these measurements are what they are supposed to be.
For the project, the next steps include bringing the deliverable to Stormy Kromer. If the project continues for one last semester, the team would have time to conclude calibrations and run any tests necessary for the proper functionality of the components. Thank you for taking the time to watch our presentation. If you have any questions, please reach out to the email recorded.